I'll put it up there so it doesn't leave. Oh, that's much better. All right. So what you see is that it was basically the universe was entirely ionized. This is the plasma era. And then right around redshift of 1100, you get this abrupt drop. And it looks abrupt here, but if you actually do the calculation of what it would be in equilibrium, it's actually not quite an equilibrium. That there's actually some freeze out going on. So this doesn't just drop down to zero, you see it kind of asymptotes, and you have this residual ionization at the level of a few 10 to the minus 4 that continues all the way down until however the universe reionized. And so this turns out to be important for any of you here doing 21 centimeters. So because there's these residual electrons around, there's a time till just around just in here where there's enough interaction between the electrons and the CMB that actually the gas stays in equilibrium with the CMB. So it's actually the temperature of the gas stays equal to the temperature of the CMB because of the details of this freeze out. So there's still some interesting stuff to do there. All right. So, but at this point right here, so up here, the mean free path for photons to electron scattering is very short. At this point, once we lose all the electrons, the photons can go streaming towards us, and we have the cosmic microwave background. So to understand the physics that we're trying to extract, I think this is, for me, the clearest demonstration of all of the physics that you need to know about the cosmic microwave background. So, so people usually show this and because to show the baryon acoustic peak. But so here's a density fluctuation in the early universe. So this is from Dan Eisenstein. And so this is just the density perturbation at a redshift of 100 years. So at a time of 100 years. So this is the very early universe, redshift of 80,000. And so what you see is they've put in a spike of density at on some small scale. So we just have a completely uniform universe. We're going to put a density fluctuation in there. And where we have a dark matter fluctuation, we're also going to have a gas fluctuation. We're going to have a photon fluctuation. We're going to have a neutrino fluctuation. This is what is known as an adiabatic perturbation. So adiabatic means that we're going to have, wherever there's extra dark matter, there's extra radiation. Wherever we're missing dark matter, we're missing radiation. Now, they've played around with the scales here, so they've normalized them all so that they all have basically the same amplitude. So a proper adiabatic fluctuation isn't exactly equal density, it's equal number densities, equal number density fluctuations. So they wouldn't naturally be completely on top of themselves. But the point is they start here, and then this is just an animated GIF. We're just gonna run it forward here. And so what's happened? Well, so why don't we run it all the way through? So you see the perturbations, the different bits evolve separately, right? So let's go back and look at, so this is at some point, so this is a redshift of 2500. So what do we have? So at a redshift of 2500, you see the dark matter is basically where it started. So the dark matter is here. You've seen it's grown out here, but what's happened is that just structure has grown. So while it's true that in the radiation dominated regime, structure doesn't grow very fast, it does grow a little. It grows logarithmically. So there's nothing stopping the dark matter from just slowly falling into that overdensity. So the dark matter peak is still there at the center. What you see here is the photon baryon fluid, and you're seeing a sound wave propagating out. And why is it propagating out? Well, because we started with a large overdensity of photons and baryons, which means that's a pressure overdensity. And so if you just start with a uniform medium, you put a pressure overdensity in there, it's going to just start expanding. So you see that that thing's expanding, and they're expanding exactly together because the mean free path is so short. So that's what you're seeing going on right here. And then here's this neutrino peak. So I think Joel's might talk about that. And what do you see here? Well, you see, oh, wait a second. Well, actually, the neutrinos are leaving the property. So they started all down here, and the neutrinos are free streaming out, and it's because this is a sound wave, and the sound speed for relativistic fluid is 1/√3 times the speed of light. These neutrinos can just free stream out at the speed of light because they're no longer interacting with everything else. So you see the neutrinos are propagating out, And that's carrying some of this perturbation out with it. And so that's going to change what's going on. So what else is going on? Well, you can see that this dark matter peak here is going to be exerting some gravity on this sound wave that's propagating out, which is to say that the details of how this thing propagates out will depend a little bit on how much mass we have in this initial fluctuation. And also how the interactions are happening between the baryons and the photons, or how many baryons there are compared to photons, are going to show up in the details of this peak. So then you run this movie forward. You get to redshift 1100, and now they've decoupled. Right? You see the photons are now starting to be able to escape, and the baryons are now stuck there. Now these photons are going to go free streaming across the universe, and they're headed out to us. And now at that point, then you run the movie forward. You see eventually the baryons fall back into the dark matter potential well, and then you get some dark matter falling into this baryon potential well, and that's the baryon acoustic oscillation out there. But all of this stuff that we're seeing before, all the things before, what you're seeing is what's going to happen with the CMB. So let's just go forward now. So what do we see? Well, we're sitting here, we're looking out. And remember, there's a surface of last scattering where everything gets released. So this is a graphic from Adam Hinks, works on the ACT collaboration. Well, so what happens is there's some surface where every one of those little peaks, you get a slice through it. And so what you would see from one of those, we would see some blob that looks kind of like that. And you'd say, okay, well, so that's for any one density peak that was out there in the universe, you would get one blob. But then, of course, there's more than one blob out there. So you start filling in the blobs. So now we're putting down more and more of these density peaks. And so it goes through a few hundred, and then it goes up to a few thousand. And then you just keep going with this. And eventually, just from putting down more and more of those blobs, you end up with something that just looks like a completely, no, let's just flip over there and cheat. You just see something that looks like a Gaussian random field. So you put down a Gaussian random field of fluctuations all over the place, and around each one of those overdensities, you have that little sphere around there. And eventually you can build up the CMB that way. So what you can think about is you can think of, you take this initial density fluctuation, and then you convolve it with these little spheres around it. And then you put it, then you have the last scattering. Say we're just going to take a snapshot of that at every spot at redshift 1100. And this is what we're going to see. And so there's two things that are going to be in there. One is whatever that initial density fluctuation spectrum is. So exactly how we distributed each one of those spheres as we put one of those little dots down, that's going to show up in what we see in the CMB. And then the details of those sound waves are the other thing we can measure. So, so that's most of what's going on in the CMB, and then everything after that is just kind of a little bit technical. All right, so here's a picture of the CMB as measured by Planck. So there's the galaxy. You're seeing we're having a few problems right there. But other than that, you're seeing just all these fluctuations. So that's the CMB. So you can think of it as a map. Or you can now go back to what we have, and you know that there is basically a bunch of density fluctuations convolved with this, these spherical shells around them. And so what that turns into is an angular power spectrum that is basically going to be something like some power law, that's whatever came out of inflation, that in harmonic space is being multiplied by whatever the shape of each one of those shells are. So you could think of, you have one of those shells. So we're all grad students, you know that whenever you have these shells, well, we're not all grad students, but we're all, at least we're once. So you know that if you're going to, you have some circular thing with edges on it, it always turns into a Bessel function. That's what Jackson tells us. Something with ringing. And so that's what you're seeing here is the ringing from those shells. So you have those shells around each thing, and the details of the profile of those shells are what are telling you the various peak heights in harmonic space. So this is the cosmic microwave background. That's the power spectrum. So I'm just going to back up a little bit and talk a little more in detail about exactly what this is. You know, just make sure we all know what these things are. So let's go back. So what is that? Well, so what we've done is we've taken the sky and we've broken it into spherical harmonics, right? So you just say, so these would be Fourier modes, except we're on a sphere. So you can't do Fourier modes on a sphere because the geometry is not right. The Fourier modes are what you want if you have something that's repeating in X and Y on a nice grid. That's not the geometry we have. The geometry we have, the complete basis here of the spherical harmonics. So you take the temperature, you expand it in these YLMs. What are these YLMs? Well, it's just some prefactor times the Legendre polynomial of cosine theta. The associated Legendre polynomial is right there. And then actually it is Fourier modes. It's just e to the im phi in this direction. So spherical harmonics in M really are just Fourier modes. And the things that are funny are if you go in theta. And so that's why if you want to do fast spherical harmonics, you're going to end up doing FFTs and phi, and you're going to just do your best to make that not be painfully slow. So you expand in spherical harmonics, these ALMs, and then what CL is, it is literally just the variance of the ALMs. So for every M, for every L, you have 2L plus 1 M's. And so you just literally are going to take ALM squared, if you had a full sky map, at every L, and you're just going to basically take the average ALM squared, and that's your CL. So it's just the variance of your ALMs. So that's CL. All right. I'm using the wrong computer. I think we'll skip that for now. What does this actually look like? Well, here's L of 20, M of 10. So I just picked this one because it's an easy one to work with. So this is your spherical harmonic. And what do you notice? Well, if you zoom in on this patch right here, it actually just looks a heck of a lot like Fourier modes. I just told you we can't do Fourier modes, but then here we are. And actually at L of 20, it sure looks like Fourier modes, especially down here at the equator. Once you start getting up there, it looks a little funny. So let's go to a higher L, L of 200. So this is L of 200, M of 100. So this is just a single ALM. What does it look like? I just put in some amplitude for it and said, what does it look like? And now it looks really a heck of a lot like just some plus minus going all over the place. It really looks like this is just Fourier modes. That's down here at the equator. You go up here, weird things start happening. And what that's saying is that you don't have uniform support for your ALMs all over the sphere. So where you put your pole can matter when you're in terms of what you're going to get for different fields. So that's weird. It sure looks like Fourier modes. What's going on? Well, let's go back to this associated Legendre polynomial equation. So if you look in the Wikipedia, I think this is literally taken from the Wikipedia for associated Legendre polynomials. Here's the equation. If you have a PLM, what equation does that solve? This is the equation it solves. Whatever. So X is cosine theta here. So that's the equation for it. And now the question is, what happens if X is close to 0, which is to say, down near the equator, right? It's cosine theta. So theta is measured from the pole. So you go back to your Legendre polynomial equation, associated Legendre polynomial equation, and you say, oh, what if X is really close to 0? Well, if X is basically 0, you get something that looks like Y double prime plus some prefactor times Y is equal to 0. And that's like the one equation I know how to solve, right? That's the one you've been solving your entire life. And that by doing exactly this, like all of physics is finding ways to make it look like a spring. So we make it look like a spring, and the solution to a spring are Fourier modes. So, so that's why if you go down to the equator, it just looks a heck of a lot like Fourier modes. And so what that means is that as long as you're down here, you actually have a choice. You could either do spherical harmonics with, say, L of 200 or M of 100, or you can find some equivalent Fourier modes to work there. And as long as you're sort of in one spot in the sky and you don't start wandering too far away, you can do that. And this is what's known as the flat sky approximation. And sometimes it makes it a little easier to do things. So if I just take this L equals 200, M equals 100, and just take a Fourier transform of the map in that part of the sky down there, it does indeed map into a single hotspot. And the decoder is that the radius in Fourier space is L, and then M is the azimuthal direction. So that's your X, basically. Your KX turns into M, and then L is your radius in Fourier space. So if you ever, and the reason you might want to do this is just because it's a lot easier to work with Fourier modes than it is to work with spherical harmonics. So if you have to do something on scales of, 50 degrees, you're probably stuck with your spherical harmonics. But if you're doing high resolution stuff, you can actually get away with this, and it simplifies the math sometimes. All right. So those are Fourier modes versus spherical harmonics. So let's keep going. So the CMB is also polarized. So this is a W map polarization map. So if you just look on large scales, especially, you can see there's some polarization vectors. So something that's maybe not appreciated is the CMB is very strongly polarized compared to the rest of astronomy. So the CMB is roughly 10% polarized, whereas radio sources are usually a few percent polarized. There's some that are super polarized, but most of them are only a few percent polarized. So the CMB is actually very strongly polarized, which means the foregrounds are not as bad in polarization as they are in temperature. And the only reason that starts to get problematic is that we're now going to insanely sensitive levels in polarization. All right, so why is the CMB polarized? So how do you make polarization? So let's see, I think the sun's out today, maybe not. But why is the sky polarized? Well, just from scattering. So whenever you get scattering from some anisotropic light source, that scattered radiation is always going to be polarized. Well, almost always. So what does that mean? Well, so let's imagine that this is your last scattering surface, and let's just make it a nice plane wave so it's easy to see what's going on. So as recombination is happening, you're now at some single point, you're now receiving light that's gone some interestingly large distance such that it's coming from somewhere where the temperature could be different. And so what that means is you're seeing further away. So some electron that's right there will start to see an anisotropic radiation field. So if you start to see an anisotropic radiation field, what that means is you can actually get some polarization. So at this spot right here, so if you're right here and you're getting, say, more radiation from here and more radiation from here, less radiation from these two spots, the scattered light that's coming towards you as you look at this is going to be polarized in the vertical direction. If this is hot over here, and if that's hot and that's cold, an electron that's right there is going to be seeing radiation coming, more radiation coming in from this side, less radiation that way. So the scattered light as it goes out to you will be up. So that's going to generate polarization. And there's basically two ways you can do it. So one is just what I just said, which is to say, as you see further away, you're just literally seeing a spot in the universe that is at a different temperature. The other thing that can happen that is a larger effect is actually you get a shear in the Doppler shift from the velocities. So basically every spot here is sliding one way or another. And so, for instance, if you're right here, if that's an O density, you have the materials moving out. So material that is moving away from you. So this material is moving away from this spot right here, if that's an underdensity. And so if it's moving away, then that's going to cause a redshifting, which means there's going to be less radiation coming from this direction than that direction. And instead, you're going to get a horizontal polarization. But notice that it's either going to be polarized vertically or horizontally, which is to say it picks out the geometry of this density fluctuation. So that's going to be super important in a second. All right, so here are some maps. So this is from South Pole Telescope. So this is from 2015. I'm using these ones because actually now our maps are large. You can see the small scale structure quite the way we can with just this 100 square degrees from 2015. So here is T, Q, and U. So that's polarization. So this is the polarized CMB. So the temperature, there's a little bit of structure there just because of the way we filter our maps. But here's Q and here's U. And I want you to just stare at those maps and try to figure out if those look right. So you look at these Q and you just see these rivers, especially in the north-south direction. And then in U, everything's tipped over by 45 degrees. So that's really weird. Why would that be what's going on? And so this gets into this idea of what are known as E modes and B modes. So what are E modes and B modes? Well, it's just exactly what you're seeing right here. What you're seeing in Q and U are E modes. So the problem with Q and U is that Q and U are defined relative to some choice. You know, someone picks which way is up, and then you say, well, I'm going to measure the electric field, say this way versus this way, and I'm going to call that Q, and I'm going to measure the electric field this way versus this way, and I'm going to call that U. But then two totally reasonable people could choose different orientations for that. So there are standards for choosing. The IU says, let's use north for Q. But that's completely coordinate dependent. And you wouldn't expect that an isotropic homogeneous universe would lead to some preferred axis like that. So another way you could define your polarization field is to just talk about which way it varies compared to the polarization direction. So what do I mean by that? Well, so what I mean is that you can pick a spot right here where you can see it's varying in the horizontal direction, right? You see that the polarization intensity, the polarized intensity is changing in the horizontal direction. And the polarized intensity changes in the horizontal direction. And for an E mode, the polarization direction is going to always be either parallel or perpendicular to the direction that it's changing. For a B mode, it's again, you see the polarized intensity is changing in this horizontal direction, but you see for a B mode, the polarization angle is actually always going to be at 45 degrees to that. So this is a pure B mode, this is a pure E mode. And so the scalars are only going to generate this E, because remember that polarization direction only gets sourced by which way the fluctuations are oriented. So when those fluctuations were going across the room, left to right, I was generating polarization either up and down or side to side, not at 45 degrees. There's no geometric way to pick out 45 degrees from some just single plane wave of temperature. All right, now the thing that's a little bit weird is that I said which way is the polarization direction compared to the direction that it's changing. Well, so remember polarization is spin 2, right? It's how much is in the vertical direction versus in the horizontal direction. It's not actually an arrow pointing up, it's either up or down. And so what that means is it's that you would think you'd say, okay, well, what's the gradient of my polarized intensity? And your gradient to your polarized intensity is, well, I don't know, is it to the right or to the left? But then on top of that, the polarization, is that up and down, or is that pointed up or is it pointed down? So a spin 2 field says that it's the same going up as going down. And so it turns out that what's going to matter is not the derivative, it's going to be the second derivative. But the E modes and B modes are all about how things are changing. So which way does the field change compared to the direction of the polarization? Or which way is it polarized compared to the direction it's changing? And so, all right. So I said that sometimes it's easier to do this in flat sky. And so and in particular, E modes and B modes are super easy in flat sky. So if you want to write down what Q and U are in the flat sky approximation, where I've just gone back to Fourier modes, and I'm just going to say the Q Fourier modes and the U Fourier modes, you can just write them down as some function E times cosine 2 phi, or that's just the angle in Fourier space, minus B. This one's E plus B. So this is U and this is Q. And so now think about what you were seeing. Well, what you were seeing in those Q and U maps, so let's just go to Q. What you're seeing in Q is a strong preference for things that are either up and down or side to side. So in this language, that's saying, well, up and down and side to side correspond to something that's either a mode that's going horizontally or a mode that's going vertically. And those are either 0 or 90 degrees. So 0 and 90 degrees are saying that you're going to get, let's go up here. All right, 0 or 90 degrees is where you're going to get a large signal in Q from E modes. And U at 45 degrees is where you also get a large signal from E modes. So what you're seeing by eye are just the E modes. All right. So the final way you could think about the E modes and the B modes is just as how the symmetry when you reflect through 180 degrees. So, all right, but that's in flat sky. Now, if you really want to do it right, we don't live in a universe where the sky is infinite and periodic. Instead, we live, it's a sphere. So just like the right way to do, strictly speaking, the right way to do the CMB analysis is to do spherical harmonics. The version for polarization are the spin 2 spherical harmonics. And so what are the spin 2 spherical harmonics? Well, you get them by just basically taking derivatives of the regular spherical harmonics. So there's second derivatives because it's spin 2. So you take second derivatives of the regular spherical harmonics. That's called the spin raising and lowering. And so they're spin spherical harmonics. Spin 1 is you're doing the first derivatives. Spin 2, you're doing the second derivatives. So you can take your polarization field and you can express it as sums over these spin 2 spherical harmonics, which, as I said, are just the derivatives. And then when you express them in terms of these spin 2 spherical harmonics, your E modes are where you take your LMs and you take the symmetric combination. So where you do 2 and minus 2 and you add them together, and the B modes are the anti-symmetric ones. So, so that's what the E and B modes are, strictly speaking. They're either the symmetric or anti-symmetric sums of the spin 2 spherical harmonics. But again, this is all about just saying which way are the fields varying compared to the orientation of the polarization, right? So this is Q and U, is telling you something about the orientation of that polarization, and then you're comparing that with the second derivatives of how these things are changing. All right, now, so I showed you that we only see the E modes in there. Well, so, and that's because for whatever reason, it doesn't seem like our universe has a lot of B modes that are being generated at last scattering. So it's not that it's impossible for that to have happened. It just turns out to not be the case. So what does that mean? Well, so in principle, gravitational waves generate both E and B. And why is that? Well, so remember that for the scalars, you just have nothing but spatially varying intensity or velocities, but everything's always going along one line. So you don't have any way to break that symmetry. So if all the variations are only in one direction, then any polarization that's generated by that has to always be in that direction. So you need something else to break the symmetry. So for a gravitational wave, what can break that symmetry is that I can have my wave propagating through the universe. So as my wave goes through the universe, so remember, it's a stretch this way and a compression this way, and then a stretch this way and a compression this way. So I could do that. I could have this stretching compression, and I can tip that over by 45 degrees if I want. But what it means is that my wave can now be propagating in this direction. And I can now have another new direction to deal with, which is the stretch versus compression of that gravitational wave polarization. And in particular, if I take a gravitational wave, and so remember what it's doing is propagating through, I take my space-time and I stretch it up, and I compress it this way. Well, that's actually going to lead to actually a red shift in the direction it's been stretched and a blue shift in the direction it's been squeezed. So I'm actually going to, if there's a gravitational wave coming through us right now, we would see a quadrupole in the CMB that's exactly what orientation that thing as it goes through. And that would cause polarization. That scattered light off an electron would lead to polarization, and that's going to pick out the orientation of that quadrupole. So we're picking out the orientation of that quadrupole and generating polarization compared to which way that stretches or the compression. And now that's changing in some other direction. And in particular, if I'm going at 45 degrees into the board, so if I had something that's going at 45 degrees into the board, I can generate polarization that is going in this direction here, but has a apparent polarization vector that's tipped over as you see it by 45 degrees. So gravitational waves generate both E and B, depending on the particular orientation of what the polarization of that wave is compared to its propagation direction. So that's the third direction that breaks that symmetry and lets you generate B modes. So that'd be great if we could measure those B modes. That's something we want to do. So here's where we are. And holy crap, we measure B modes. Look at that. There's all sorts of B modes here. Well, so these are the wrong B modes. These are lensing B modes. So we'll do that tomorrow. So I'll do some lensing B modes tomorrow. So the B modes from inflation are these ones here. These ones up here are the lensing B modes. And what happens is as you propagate through that lumpy universe, that breaks that nice boxy symmetry. There's no reason that gravitational lensing is going to respect that symmetry. So the lensing distortion of that nice E mode symmetry is what gives you these B modes. But here's where we are right now in terms of CMB power spectra. So you see T's measured extremely well. So Planck, so it's a weird axis. So people be careful with these axes when you look at things. People do weird things. You see it's linear here out past 1,000 and it's log before that. So, and you know why, it's done because otherwise you would see either just the stuff out here or just the stuff down here. So it's kind of a compromise. You can see some of the weirdness that's going on where you see, people want to argue about whether there's problems there. But the thing that you should get out of a plot like this is that the temperature spectrum is measured extremely well. There are error bars on these points, but you see they all kind of run out of gas around 3,000. And you might think, well, that's weird. Why do they all run out of gas at 3,000? It's not because we can't measure the sky at higher resolution than that. It's just that once we get out to L of 3,000, we're starting to run into confusion from foregrounds, in particular dusty galaxies and radio galaxies, galaxy clusters. So the sky starts getting a little messy once you get out to around L of 3,000. So people are not quite as ambitious about putting plot points down with error bars out there. In the E modes, so this is the polarization, what you see. So Planck starts to run out of gas right around here. The ground-based stuff really kicks in. And you see they get out to about L of 3,000. But now you can see why they stop. It's because error bars are becoming not zero. So basically, we're limited by signal to noise out at L of 3,000 in polarization. And remember I said the CMB is way more polarized than foregrounds. What that means is that we could actually keep going out to probably L of 5,000 in polarization and not have to worry about foregrounds. So there's actually lots to do in CMB out here. So in the polarization at high L, we basically have as many modes unmeasured in polarization out here as we've used to do all the cosmology to date using the lower L temperature. So there's still lots to do in CMB. Like sometimes people are like, oh, CMB is boring. There's nothing left. Yeah, we could do it all like again. And that's pretty good. The first time was good. Why don't we do it again? And then the other thing to do is to go after these polarization B modes. And what you see is just the tyranny of how small the signal is. This is in microkelvin squared. And you see these signals could reasonably be measured in a unit of nanokelvin. And that's just a really small signal. And so that's why you see the measurements that have been made, they're pretty good, but they're still a little bit noisy. And so these points right here are the bicep Keck points. And so they're the people that currently have far and away the best large angle measurements. But even then you see there's some reasonable error bars on there. So the new front, a lot of the new work is being done down here, going after this R signal, and out here to try to get a whole new CMB. All right. Now, so what I haven't talked about, but what I thought would be fun to do would be to just kind of noodle around with, get people using CAMB afterwards. So after the break, we're going to hope there are enough people with laptops here that this will actually work. We'll see how it goes. What we're going to do is we're just going to have some fun with running CAM and just looking at the 2-point correlation function and trying to understand what's going on. Because remember, I showed that bump, right? That propagating peak. So that propagating peak is there, and it must be there in the CMB as well. And so when you see it done with BAO, you see that nice peak there, and you're like, oh yeah, that's a good peak. So let's just do the same thing with the CMB, because it's actually something people don't plot very often. If you would just Google like 2-point correlation function of the CMB, I almost guarantee you will not be able to see the acoustic peak in that 2-point correlation function. All right, so what is the 2-point correlation function? Well, it's exactly what it sounds like. There's 2 points. You take the temperature at 2 points in the sky, T N1 and N2, and you just multiply them together. And if they're uncorrelated, then if you take the average of that, you'll get 0. If they're strongly correlated, then those will keep adding up. And so the 2-point correlation function is telling you something about the general coherent scale of the structure that you're looking at. And so N1 and N2, these are just 2 different spots in the sky. You can take their dot product, that gives you some angle. And so you can then do this as a function of theta, where theta is the separation between these 2 things on the sky. And if you calculate what this thing should be, it should just be basically 2L plus 1 over 4 pi times this weighted sum of your CLs. All right, so what I propose we do is, so I'll take some questions now. And then after the break, so what I did is I put together a collab notebook and so it's one of these, it depends on I'm not sure exactly where everyone is in terms of having used these. You can go as deep into this or as shallow into this as you want. But what it'll do is it'll basically install CAM for you. So you hit enter, you get CAM, you can generate a power spectrum, you can look at it, and then calculate a 2-point correlation function and try to understand what it means. And then from there, just play around with it and see what happens. All right, so questions? Well, it's more information. So you can see there's still peaks out here. There's still all the peaks. So we still get all the peaks. And if you look in the temperature in the TE correlation, it's a little clear. But so you'll get more of these peaks, which means you just get a lot more precision about the details of what was happening at decoupling. And so one of the things that shows up there is stuff about, remember he showed those neutrinos were getting ahead of us. So that leads to some small phase shift because you're actually moving things, some of that mass density is actually getting carried away. And so it actually leads to some slight time-dependent change in the gravity within that peak. And so, so you get that by just looking at more cycles of the ringing. So there's things about recombination will show up out here. So, because remember, the details of recombination tell you exactly how decoupling happened. And so there's silk damping that happens because you have these sound waves. And so a sound wave, you have something that squeezes and then it rarefies. So you have these propagating sound waves. As the mean free path starts to become interestingly large, you squeeze it and things diffuse out. And so the acoustic oscillations get damped on small scales. And the amount of that damping is going to be sensitive to how that recombination process happened. So there's physics in there. And so I don't think we're going to talk about it tomorrow, but the other thing that's out here is a whole zoo of second order effects. Because this is where you get, because you can get all sorts of E turning into B from any propagation effects. So for instance, if you go through a cloud of electrons, that'll scatter things out of your beam, and that causes EB correlations in some interesting way. So I don't know if there's a lot of inflation stuff out there. I don't think we're gonna learn anything about inflation from out there, but maybe Joel can take that one up.
Let's take maybe just a short break, so that we leave enough room for lunch. We can bring it up after. Yep. Short break, few minute break, flashlights, bathroom. So this call that, this is super interesting.